So for this lecture, we are going to discuss examples of pavement design for Unit 1 and 2 of Module 5, which covers the topics of flexible and rigid pavement design. So to start off, let's have example number 1 for flexible pavement design procedure. So we have a pavement is to be designed to last 10 years. The initial PSI is 4.20 and the TSI is determined to be 2.5. So the subgrade of the pavement has a soil resilient modulus of 15,000 PSI and will have a reliability of 95% with an overall standard deviation of 0.4. So for our design, we now have a daily traffic, or we would expect a daily traffic for the pavement for cars, pickup, truck, and light vans to be 30,000, in which this type of vehicles will be 2,000-pound single axle vehicles. And then we have 1,000 single unit truck traffic, in which they have an 8-kip steering axle and a 20-kip drive axle. So the steering axle is a single axle load and the 20-kip drive axle is a tandem axle. Okay? And then for the next type of vehicle, we have 350. So we're expecting 350 per day traffic for tractor semi-trailer trucks, which have a 10-kip steering single axle, 16-kip drive tandem axle, and a 44-kip trailer triple axle load. So aside from that, we are given M2 and M1 for our pavement structure for your sub-base and your base to be equal to 1.0 for our materials, in which 4 inches of hot mix at asphalt is to be used for the wearing surface, and we have 10 inches of crushed stone for the sub-base. So in this problem, we are to determine the thickness required for the base if we are going to use a soil cement or soil cement as our material for the base. So to start off, we are given now the following, or we summarize the following given. So we have a design life of 10 years, a PSI or initial PSI of 4.2, terminal service index of 2.5, resilient modulus 15,000, reliability of 95%, and overall standard deviation of 0.4. So from the reliability, 95%, we can now use our table for the reliability in order to get the value of ZR. So the reliability here is 95. So from 90, we move to 95. So the reliability or the ZR, corresponding ZR for our reliability is now equal to negative 1.645. Okay, so that's one of our givens or our required value in order to solve for our thickness. Okay, so since one of the controlling factors for flexible pavement design equation is the structural number, and if we're going to take note, the axle load equivalent factor is a function of that variable S sub n. And S sub n now will be dependent or will require the thickness of the layers. So in this case, or in this problem, we are required now to solve for the thickness of the base, which is D sub 2. So therefore, we cannot solve Sn directly. So in this case, we have to assume first a value of Sn. Okay? So After assuming the value of Sn, we are going to check it later if it is consistent with our assumed Sn. So we are going to assume and then compute for Sn, and we are going to compare them if they are consistent with each other. So in this case, a typical assumption now of Sn is equal to 4. So once we have established our assumption of the structural number, next step is to check now the equivalent axle load factors, or your ESEL or ESAL, for each vehicle that will pass our pavement to be designed. Okay. So for our problem, we are given 30,000 traffic for car pickups having two 2,000-pound single axle. Meron tayong 1,000 single unit traffic with combination of single axle. And then we have your tractor semi-trailer trucks with 350 daily traffic with a combination of single, tandem, and triple axle loads. So to solve now for our equivalent single axle load, we now use table 4.1 from your module, which is taken from the Ashtory guide for design of pavement structures. So let's start off first with the first type of vehicle, the car, pickup truck, and light van with a single axle. So table 4.1 is used for getting the equivalent factor for single axles. And if you remember, the given TSI in our problem is 2.5. The TSI is not 2.5, then we will not be able to use table 4.1. So in this case, the condition for table 4.1 is follows: 2.5 TSI and single axle. So with that, we now have equivalent 2,000 pound, or that is 2 kips. And then our pavement structural number, we are assuming that it is 4. So all values will be taken under this column. So for the 2,000 pound single axle, that will be under this row, 2 kips. So 2,000 pound is 2 kips. So intersection will now be equivalent to 0.002. So why did I multiply it by 2? Because it is given that the car, pickup truck, and the light van consists of two 2,000 pound single axle. Okay? So, big sabihin, dalawang single axle yon, so I have to multiply it by 2, giving us now a total equivalent single axle factor for the first type of vehicle equal to 0.004. Okay? So next, we have our single unit truck vehicle, in which it is a single axle, 8 kip. So hanapin ko lang siya dito sa table. So single axle pa rin siya, so we can still use table 4.1. And we look now for the row of 8 kips. Therefore, it will give us a factor of 0.041. Still under your single unit truck, it has a 22 drive single axle load. So we still use table 4.1. Look for the 22 kip row. And from here, we are able to look now or get a value of the factor 2.09. So adding up the factors for our truck, that will simply be 0.041 plus 2.09. That is equal now to 2.131. And then, for the next vehicle type, our semi-trailer truck, we have a 10 kip single axle. So we still use table 4.1. So 10, giving us a factor of 0.102. Okay? So we have already found all the equivalent factors for the single axle loads for each vehicle. So meron tayo tandem saka triple axle. So this is table 4.1 now will not be applicable for tandem and triple. So what we will do is to use now a new table, another table for the tandem axle, which is table 4.2. So again, our structural number that we are going to use in our design, as we have assumed, is 4. So all values will be taken under Sn equal to 4. So hanapin lang 16 kip. So that will give us 0.057 factor for the 16 kip tandem axle. And then for the triple axle, so for the triple axle, we now use a different table again. So the triple axle will be using 4.3, table 4.3. So check nyo lagi yung title dito. So triple axle 44. We have now here 44, which gives us the equivalent factor of 0.769 under structural number 4. So for the semi-trailer truck, add up all the equivalent factors. So this will now be equivalent to 0.928. Okay? So pag nakuha na natin yung total equivalent single axle factor for all the different types of vehicle traffic for our design. Next is to compute now for the equivalent daily weight of 18. So we have 0.0004 times the total traffic of 30,000. Then we have for the truck, single unit truck, that will be 2.131 times the number of traffic, which is 1,000. And then for the semi-trailer truck, that is now 0.928, yung total nito, times the traffic of 350. So from there, our total daily W18 equivalent single axle load is equal to W2467.8. Okay, so once you have solved for your total daily equivalent load or total daily traffic, so we compute for the accumulated axle load in 10 years. So we compute that simply by multiplying your daily traffic by 10 years. So that will now be 2467.8 times 365 days. So this is per day. So times 365 para mag-cancel out yung day. So times 10. So in 10 years, the total axle accumulation is equivalent to 9,007,470. This is the total traffic supposedly in 10 years. So with that, we have our delta PSI since we need it in our equation. So TSI minus PSI lang yon. So that will be 4.2 minus 2.5, which is equal to 1.7. Other given for our, so solving now for SN using our equation, using the other givens. So we have what we have taken a while ago. ZR for 95% is negative 1.645. Our MR, resilient modulus, is 15,000. And our overall standard deviation is 0.40. So since we were able to compute now for the accumulated traffic of on the pavement equivalent to W18. So also using the summarize given from the problem. We substitute these values now in our given equation. And from there, we could now apply iteration. So substitute, and then by iteration or by a simple trial and error, will now arrive at the value of Sn, or the structural number, equal to 3.9401. So in this case, we can now approximate our computed Sn equal to our assumed Sn of 4. So if we want to have a more accurate answer, we could recalculate the accumulated axle load using 4.1, 4.2, and 4.3 tables by interpolation. And then we again compare our assumption and our computed. So basically, it will be more accurate. So in case that the computed structural number is not equal or approximately equal to the assumed structural number, then we have to recompute the structural number again, and likewise we have to get the accumulated traffic load again using a different value of Sn. But we will still follow the same procedure. So for example, the Sn computed here, let's say, is 3.1. So this is, we cannot approximate it as equal to 4. So, ang gagawin nyo is to repeat again from the start. So instead of using the values found under column 4, we now use the values found in column 3 or SN3. Tapos same procedure, look for the equivalent factor, and then compute now for the daily traffic, compute for the accumulated traffic, and then substitute in this equation, trial and error. So dapat yung makukuha nyo ng Sn should be the same or approximately equal now to the previous computed S sub n. Okay? So we'll have other examples later on that would deal with the same problem. So if our assumption is different from our computed value. Pero in this case, 3.94 is approximately equal to 4, so we stop at this value already. Take note, So since we have computed already for the value of d sub 2 or the thickness of the base, another or an additional question for example number 1 is what would be the most economical pavement thickness for our flexible pavement? Okay, so we have the first option is to use our computed d sub 2 in our solution, wherein that's now 5.5 inches. So the given in the problem is 4 inches. D3 is 10 inches. So D4, D1, and D3 are from the problem. D2 is our computed value. So if we're going to add up the thickness, the total thickness now is 19.5 inches. So it's kind of very thick. As we all know, pag makapal yung layers natin, it could be expensive. So what we will do is to have another option. So option 2 is that instead of using the given 4 inches from the problem, we now assume it to be the minimum thickness of the wearing surface, 2 inches. So if that's the case, we now follow the equation for the structural number using our computed SN 3.94. So still same materials. So we have 0.44 times the new or the assumed D1, 2. And then we compute for D sub 2, in which we'll get now a value of D sub 2 equal to 10. So in that case, the new computed D sub 2 is 10 if the wearing surface is 2 inches. D3 is the same, 10 inches. So if we're going to solve for the total thickness, that will now be 22 inches. So, mas malaki siya compared doon sa option 1. So, we could try another option. So, another option, 3, is to change now the material of the base. Instead of using soil cement, we now use hot mix asphaltic concrete with a new thickness of D1, which is still 2 inches. So again, we apply your structural number equation. And with that, we will need now our coefficient for hot mix asphalt concrete for the base, which is 0.4. So applying now this coefficient to your SN equation, still using our computed SN 3.94. So 0.44 times 2 plus 0.4 d sub 2 times 1 plus 0.11 times 10 times 1 will be able to get D2, which is equal to 5 inches. So in that case, we have now the new layers or thickness of the layers at 2 inches, 4 inches, and 10 inches. So, pag sinolve natin, we'll have now a total thickness of 17 inches. So, basically, between options 1, 2, and 3, we now have for option 1, the remaining choices will be option 1 with 4, 5.5, and 10 since ito yung sumusunod doon sa given natin sa problem. And then we also have option 3 with a different material for A2. Okay. So, which of option 1 and option 3 will I use now? So, what I will use here will be option 3. So, this will now be the preferred pavement thickness since there will be lesser thickness. Okay? So, lesser thickness but still it follows our structural number of 3.94. But, considering the material cost, the labor cost, the availability of material, number of working days, and other factors in our selection, we could use option 1 if option 1 is cheaper compared to option 3. So kahit lesser si option 3 in thickness, pero kung mas mura si option 1 ang gagamitin natin. So in design, for economical design for our pavement thickness, so it should follow your structural number computed, or the structural number. Tapos, we will choose the lesser thickness or which is cheaper. Now, example number 2. So, flexible pavement is constructed with 4 inches of sand mix asphaltic concrete, 8 inches of soil cement base, and 10 inches of crushed stone subbase. The subgrade has a soil resilient modulus of 12,000 psi. M2 and M3 is equal to 0.95 and 1.0 respectively for the materials in our pavement structure. The overall standard deviation is 0.6 and the initial PSI is 4.2 and the terminal serviceability index is 2.5. So we are given daily traffic of 274, 24 kip single axle, 219, 32 kip tandem axle, and 524, 40 kip triple axle. So how many years is the estimated life of the pavement if you are 95% confident that your estimate is not too high? And how many years will the pavement last if we are 90% confident that the estimate is not too high? So in this case, given tayo ng thickness for all our layers, so we are not going to assume the structural number anymore because we can solve for Sn. Okay? So given now 4 inches of your wearing surface, 8 inches for the base, and 10 inches for the crushed stone. We're given the different materials and we're given M2. So for the wearing surface, it's sand mix asphalt. So we are going to use now our A1 equal to 0.35. It's a soil cement base. So our A2 is 0.2 and our sub base is equal to 0.11. So just substitute the values. Sn now is equal to 0.35 times 4 plus 0.2 times 8 times M2, which is 0.95, plus A3 equal to 0.11 times the thickness 10 times M3 equal to 1. So in this case, our structural number is 4.02. So in this case, we can approximate this as equivalent to 4.0 para hindi na tayo mag-interpolate. Okay? So with this, we can now solve for our equivalent factors. So for single axles, we use again table 4.1. The given TSI is 2.5, so this is applicable. So our structural number is 4. So for a 24 single axle, that will now give us a factor of 2.89. And then next, we move on to the tandem axle, in which we are going to use table 4.2. So 32 kip under structural number 4. So that will give us 0.887. And then we have for the triple axle, we use table 4.3. So for 40 kip under structural number 4, we have now an equivalent single axle load factor of 0.533. So from these factors, we can now compute for our total daily traffic, or W18 daily, by multiplying the number of traffic by the factor. So 274 plus 2.89 plus 219 times 0.887 plus 524 times 0.533. So the total daily traffic now is 1,116.698. So from there, we have the other given from the problem, your structural number, 4.02, your S sub O, or your overall standard deviation, 0.6, PSI is 4.2, PSI is 2.5, MR is 12,000. So we use this equation to solve now for the design W18. So substitute the values. So if the design life is 95%, so we are 95 confident in our design life. So we now have a ZR of negative 1.645. So substituting now, we have ZR negative 1.645 times 0.6 SO. SN is 4.02 plus 1. So PSI is 4.2 minus 2.5. So SN plus 1 is 5.02. MR is 12,000. So we'll now be able to get log of W18 is 6.45. For our design, W18 for our pavement is 2,866,818.863. So given now our total, or your accumulated traffic for the entirety of the life of the pavement, and given our daily W18 for our number of years, that will now be equivalent to your design divided by the daily axle load. In this case, we will be able to compute for the design life equal to 7.03 years, or approximately 7 years. Okay? So that is the year of life or design life pag 95% confidence. So for the next problem, still using the other or same given in our problem, in our computed daily. So ngayon, we are now 90% confidence or confident in the design. So we now look first for our Z sub R in our table. So 90, ito yon, which is negative 1.282. Okay, so again, this is negative values, lahat to, ha? So with that, same process lang, substitute natin, ang magbabago lang doon will be our Z sub R. So substituting all our values in the equation, we'll be able to get log of W18 for a 90% confidence as 6.6752. So W18 now is 47, or that is 4,733,694.796. This is the accumulated or total axle load for the entirety of the design life. So same process, design load divided by your daily load. So we get a value of 11.614 years. So if you're going to notice, a lower confidence level will yield a higher value of design life. Okay? So ibig sabihin, pag mas mataas yung reliability or yung confidence level natin sa design natin, nagiging conservative tayo. Ina-assume natin na mas, or parang nangyayari, mas mababa yung, mas maiksi yung lifespan ng ating, or design span, or yes, lifespan ng design ninyo. Okay? Okay, so we have the Ashtory rigid pavement design procedure. So let's have example number 1. We have a rigid pavement is to be designed to provide a service life of 20 years and has an initial PSI of 4.4 and a TSI of 2.5. The modulus of subgrade reaction is determined to be 300 pounds per cubic inches. For design, the daily core pickup truck and the light van traffic is 20,000. The daily truck traffic consists of 200 passes of single unit trucks with combination of single and tandem axles and 410 passes of tractor semi-trailer trucks with single, tandem, and triple axles. The axle weights would be for car pickups and light vans will be 2,000-pound single axles. For a single unit trucks, it will have 10,000 single axle, steering axle, and then 22,000 tandem drive axles. Tractor, semi-trailer trucks will have 12,000 single steering axle, 18,000 tandem drive axle, and 50,000 triple trailer axle. So in our design, we'll have a reliability of 95%, an overall standard deviation of 0.45, and we'll follow that the concrete modulus of elasticity is at 4.5 million pounds per square inch. Modulus of rupture of the concrete is 900 pounds per square inches. Load transfer coefficient is 3.2, and that we have a good drainage condition, giving us drainage coefficient equal to 1. So in this problem, we are to determine the required slab thickness. So similar with the flexible pavement design, we start off again by identifying our equivalency factors for each of our vehicles. So in this case, for all of our vehicles, they are consisting of single axles. So in this case, we are going to use table 4.6, which is our equivalency factor for rigid pavements for single axles with PSI of 2.5. So in this case, in rigid pavements, our controlling factor will be the slab thickness or D, while for the flexible pavement, as we have used, is the structural number. But since in this problem, we are to identify or solve for the thickness of the slab, we are now going to assume our D. And a typical assumption for rigid pavement will be a D equal to 10 inches. So therefore, under the column 10 inches, we now look for the equivalent factors for the 2,000 pound, 10,000 pound, and 12,000 pound single axles. So we'll have for the 2 kip, that is 0.002. For the 10 kip, we have 0.081. For the 12 kip, we have 0.175. So with this, we compute now for their equivalent weights by multiplying the equivalent factor to the number of vehicles passing. So for cars, pickups, and light vans will have 0.002 times the number 20,000. And consider we have 2,000 pound single axles, so we have to multiply it by 2. And then we have for the 10,000 pound steering single axle of the single unit truck, the equivalent single axle load in terms of 18 kips would now be equivalent to 0.081 times 200. And for the semi-trailer truck, the equivalent single axle load in terms of 18 kip will be 0.175 times 410 trucks. So next, we move on to the tandem axles. So for the tandem axles, we'll now be using table 4.7. Still, we follow the column under 10. So for the 22 kip axle, we have 0.305. So multiply to 200 to get the equivalent single axle load in terms of the W18. And then for the 18 kip tandem axle, we have 0.132. So multiply it by 410. And then lastly, we have the triple axle, wherein we are going to use table 4.8. Under 10 inches thickness, we have the 50 kip axle load. Equivalent factor is 3.02. So multiply this by 410. And then to solve now for the total daily traffic in terms of W18 or 18 kip axle, that will now be simplify 2 times 0.002 times 20,000 will give us 8. And then next, we have 0.081 times 200, 16.2 plus 0.305 times 200 is 61 plus 71.75 plus this value is 54.12 plus this value is 1238.2. So the total daily 18 kip axle load is equivalent now to 1,449.27. So from using now this rigid pavement design equation, we were able to solve our daily W18 1448.29. So we need to get the value of W18 by simply multiplying or accumulated W18 by simply multiplying your daily traffic by 365 times the design life, which is now equal to 100, or that is 10,579,671. And then other given that we are going to need for this equation, we have your ZR at 95% is negative 1.645. PSI is at 4.4. TSI is 2.5. K is 300. Standard deviation is 0.45. Modulus of elasticity is 4.5 times 10 raised to 6. Rupture is 900. Load transfer is 3.2. And drain coefficient is 1. So substituting now all our values in our rigid pavement equation, we can simplify our equation. So log of 10, 57, 96, 71 is 7.02447. So we have here our long equation. So it's kind of hard to simplify our long equation. So to solve now for the thickness D, what we are going to do now is to apply iteration, which you have learned from your numerical methods, or by trial and error. So you can tabulate this with the trial value of D and the equivalent log W18. So we have assumed a value of D initially at 10. So substituting 10 in D for this equation will give us log W18 of 7.24251. Compare this to this value, it's not equal. So therefore, our D is not equal to 10. So let's try other values. Let's say 9. So substitute 9 in our equation. So we'll arrive at 6.96513, which is lower compared to this value. So meaning, our value now of D will be between 10 and 9. So let's have the midpoint of 10 and 9, so 9.5. It will give us 7.10622. So meaning, hindi pa rin siya equal. So 7.02 is between 9 and 9.5. So we could use 9.25, which will give us 7.03627. So checking our value, it is still not equal, but almost near 9.25. So 7.02447 is between 9 and 9.25. So we could probably use a value of 9.2, which will give us 7.02214. So malapit na, pero hindi pa siya sakto. So we could use another trial with 9.23, which will give us 9.03062. So it's a little bit higher than what we want to have. So probably it's basically between 9.2 and 9.23. So let's try another one, 9.215, which will give us 7.02643. So it's almost there. We have between 9.215 and 9.2. So probably we could use 9.207. So it will give us 7.02417. Furthermore, let's try 9.208, which is 7.02440. So we could stop here, or if we are using Excel in solving this one, or you could use your calculator, a value nearest to 7.02447 is equivalent to 9.20825. So this is the more exact or more accurate value of D that will give a log W18 of 7.02447. So take note, our computed D is 9.208. Our assumed value is 10. So it's too far from our assumed value. So what we have to do is to recalculate our daily traffic by using D equal to 9.0. So we start again with the first step. So again, we find our equivalency factors for the single axles, tandem axles, and triple axles using the values under D equal to 9. So for our single axle, again, we use table 4.6. So under 9, we have 2 kips, we have 10 kips, and 12 kips. So solving now, the equivalent load, we have 2 times 0.002 times 20,000. So here we have 0.082 times 200. And we have here 0.176 times 410. So next we move to the tandem axle. For the single unit trucks and the semi-trailer trucks. So again, we use table 4.7. So under slab thickness 9 inches, we have 22 kips, 0.308. So times 200. And then we have 18 kips. We have 0.133 times 410. And then lastly, we have our triple axle. So using 4.8, so under 9 inches, we have 50 kips. We get 2.94. So again, multiply that by 410. So solving these equivalent values and adding them up, we get the total daily weight of 18 kips equivalent single axle load as 8 plus 16.4 plus 61.6 plus 72.16 plus 54.53 plus 1205.4, which is totaling to 1418.09. So same process, using now or will now be using the rigid pavement design equation. So we have to solve first for the accumulated traffic using our daily W18 by simply multiplying it to 365 and the design life of 20, which will give us 10,352,057. So some of our givens will be unchanged. So ang magbabago lang will be the W18. So ZR still negative 1.645, PSI still 4.4, TSI is 2.5, K300, standard deviation 0.45, EC is 4.5 times 10 raised to 6, S sub C is 900, J is 3.2, and CD is 1. So substitute these values in our equation. We get now log of 10,352,057 is 7.01503. So again, we cannot simplify this, the right side of the equation, so we will be using iteration or trial and error. So trial and error by adjusting or changing the values of D so as to arrive with the value of 7.01503. So our assumption in this case is 9, and we were able to solve it a while ago at 6.96513, which is far below what we want to have. So meaning it's higher than 9. So the final value that we were able to compute in the first trial using 10 inches was 9.20825, which gave us 7.02440, which is above our required value. So with that, let's use a value between 9 and 9.208. So let's use 9.2. We were able to solve this already a while ago, and it was 7.02214. So it's still higher than 7.015. So let's try 9.15. This will give us a value of 7.00796. So it's kind of lower. So it will be between 9.2 and 9.15. So let's try 9.175, the midpoint, which will give us 7.0505, almost near. So we could stop here, or if we want to get exactly 7.01503, we could try other values such as 9.74, but it will be giving us 7.01477. So probably we could use 9.1745. Still 7.0149. So try ko 9.1749. So it's very near already. So let's try 9.7491. So it's exactly the same. So therefore, our D now for the rigid pavement design is 9.17491, which is almost equal to our first computed value using our assumption of 10, which was 9.20825. And if we're going to compare it with our assumed value of 9, it's also almost equal. So we could accept this value already. So in that case, we now round off our computed D to the nearest 0.5 inches for a conservative design. So we round it up to 9.5 inches. So this is now the required thickness of our rigid pavement for the following conditions for example number 1. Another example, we have in 1996, a rigid pavement on the northbound section of Interstate Highway was designed with a 12-inch PCC slab, an EC of 6 times 10 raised to 6 pounds per square inches, a concrete modulus of rupture of 800 pounds per square inch, a load transfer coefficient of 3, initial PSI of 4.5, and a terminal serviceability index of 2.5. The overall standard deviation was 0.45. Modulus of subgrade reaction was 190 pounds per cubic inch, and a reliability of 95% was used along with a drainage coefficient of 1.0. The pavement was designed for a 20-year life, and traffic was assumed to be composed entirely of tractor semi-trailer trucks with one 16-kip single axle, one 20-kip single axle, and one 35-kip tandem axle. The effect of all other vehicles was ignored. The interstate has 4 northbound lanes and was conservatively designed. How many tractor semi-trailer trucks per day were assumed to be traveling in the northbound direction? So, to solve for our required, so given now all the given data from the problem, we first identify our reliability, Z sub R factor, which is negative 1.645 for a 95% confidence. And from tables 4.6, 4.7, and 4.8, we can now identify our equivalent factors for a single and tandem axle. So for a 16-kip single axle, we'll have an equivalent factor of 0.599. And for a 20-kip single axle, we have a single axle load factor of 1.59. And a 35-kip tandem axle will have a factor of 2.245. Take note that in table 4.7, we only have factors for 34 and 36. There is no factor for 35. So what we have to do is to interpolate the value between the factors under 34 and the factor under 36. So these factors are under the 12-inch thickness. So interpolating will simply be taking the average of 1.97 and 2.52. So from here, we just add them up to get the total equivalent single axle load of 4.434. Okay, so after that, we now apply our variables or our values in our equation for a rigid pavement design. So substituting all this value, we are able to get log of the equivalent axle load for 18 kips as 7.59923. Taking the anti-log of this value, we get W18 or total W18 or the accumulated traffic for the entirety of 20 years is at 39,740,309 vehicles or passes. And then from here, we can now take the daily W18 by simply dividing the total or the accumulated traffic by 365 and the design years of 20, giving us a value of 5443.878. And from here, we could take now the number of trucks by dividing the daily traffic by the total equivalent single axle load, thus giving us a value of 1227.7578. So this is the total number of trucks passing our pavement. But take note that we are required to identify the number of tractors passing in the north direction. So in that case, we're going to use now this table from your module, which gives us the proportion of directional traffic in a pavement. So from the problem, it is a 4-lane highway. So we are going to use a PDL of 0.5 to 0.75. So in this case, we are going to use the maximum value, which is 0.75. So therefore, the directional weight now, or the directional traffic, would be the number of trucks divided by the PDL 0.75, in which our answer or the required answer now for the problem will be equivalent to 1,637.01 or approximately 137 or 1638 vehicles passing in the north direction. So that's it for our examples for pavement design for flexible and rigid pavement. So thank you for listening.